Welcome to Speck&Tech. It's a special event because it's our 50th. A big applause. It's kind of magic when you feel it. Like it's been ages. We were saying since 2019. Oh my God, we're getting close to the number 50th. And then yeah, COVID hit, and we had to kind of reinvent ourselves. What's Speck&Tech for the people who are brand new here tonight? We're a community. Like today, like we are a group of people gathering in a room. We started back in 2016. We grew a lot. We got a bunch of speakers from all around Italy, Europe, and the world. And as you can see, we grew a lot also in the numbers. We managed to get more than 100 people. Of course, for the records, we are 99 people tonight. After the events also came the spec and the beers. And if you're staying here tonight, later on, otherwise, if you need to go home, feel free, but there's going to be more food for the others. There's going to be a long break, a long networking session with the people you like, meeting new friends, meeting new people. Also, if it is your first time here at Speck&Tech and you would like to meet new faces, you can go and meet in this corner, and we'll try to gather newcomers, first-time speakers at our event. The association is managed by this current board at the moment, so it's 9 people, but it's gathering more and more participants, more people involved. So if you'd like to contribute in any of our initiatives, feel free to come and talk to any of us. We are those wearing the T-shirts, like anyone in this room, actually. But yeah, feel free to come and talk to us. And there's a number of new initiatives that we're launching, that we have launched. Last year, we had our first Speck&Trek, who's a brand new initiative. We had already 3 issues, and we basically go hiking with the people from the community, and then we talk tech, and then we drink tea and beer and eat panini with Speck, which is always a good option. Second, we started a new initiative called Alfabetizzazione Digitale, also called Progetto Anziani, also called Il Smartphone, which is basically a workshop for older people, you might say, or people that are very newbie to the current technologies. I would like to know more about that. And we teach them how to survive in this waterfall, in this ocean of cookies, of hackers, of scam, of ads, etc. So, as you said, there's a bunch of initiatives that you can contribute to. So if you would like to join the association or contribute somehow, just get in touch with us. Tonight, as we were telling you, it's our 50th event, and it's quite special. And as you can see, we got a brand new, you can say, identity or a new branding to promote the event number 50th. And we will be talking about space tech in particular. And our first speaker of the night is CARLO ZANONI from the Istituto Nazionale di Fisica Nucleare. A big applause. I wasn't prepared at all to say that in English, so yeah. The second speaker, a warm applause for Linda Mazzotti from Primo VC. And the third speaker is here, sitting here nearby, quite easy, Mattia Varile from Icospace.
Whoops. Okay, so after the talk, there will be the networking part. So there will be spec and beers for everybody. We do not charge you for anything.
Yes, we do.
Yeah, but you can still support the community. So how can I support Speck&Tech? First, you can buy our beautiful T-shirt. There are some T-shirts there at the entrance, just few of them. We are already working on the new T-shirt for this year. You can grab some stickers, and you can put them wherever you want. I mean, on your laptop, smartphone, or, well. Or you can go at the desk at the entrance where there is Sam or Nick and donate us. We accept Satispay, cash, and even card payment. And we have also a beautiful website where you can find, information regarding upcoming events, and you can find also the material of the past events. If you want, you can contact us. If you want to be like the next speakers for the next event, or you want to sponsor a Speck&Tech event. And yeah, we have a dedicated section on the website where you can find open position from our sponsor like OpenMove. And we have a dedicated link for the Invest in Trentino portal where you can find high-tech job position for companies supported by Trentino Sviluppo.
So even if you're not a developer, but you're a mechanical engineer or something in between, there's plenty of jobs out there. So just go on our website or tell your friends or tell your, I don't know, cousin or mother, whatever, and go to our website. There's plenty of job opportunities out there. There's no need to go to Milan. So, sorry about that.
We are also on social networks, so we are on Telegram, Facebook, Instagram, Twitter, and LinkedIn. And this is very important. So after each event, we will send you an email with a form where you can give us feedback. We really care about your feedback because we really want to improve Speck&Tech after each event. So if you have anything to share with us and you think that there is something that we can improve, please tell us. And we are already working on the next month event, so be ready for that. We don't have a date yet, but we are kind of close.
We can give you two spoilers.
Yeah.
First spoiler, it might be on the 20th, or maybe not, but yeah, on the 20th. And what's going to be about?
Logistics and planning.
And planning and routing and, yeah, trucks.
Yeah.
Quite cool, yeah.
And yes, so we are ready to start with this event. If you have any question or you want to share any thoughts during the presentation, you have to go to Slido/spec50 and you can write anything there. So I think we can start. A big applause for the first speaker of the night, CARLO ZANONI.
Thank you for the introduction and welcome to the first talk of this evening. So the topic of this talk will be like large science projects and especially how to build them and how to build them in space. So to warm up a bit now at the beginning, so you probably all have an idea of what is a space exploration project. And so I put here a few pictures. So I start with Voyager. We have Opportunity, the rover on Mars. We have the Hubble Space Telescope. And we have Rosetta, that is one of my preferred ones. So if we focus only on science and on the European Space Agency projects, so because there will be a difference between exploration and science, don't ask me about it. But this is the range of missions that the European Space Agency has flown, is flying, or will be flying. And so the goal of my talk is to give you an idea of how these projects are conceived and developed. And so I cannot talk of, I cannot generalize too much. That's not my job. But I work on one of these missions, that is this LISA here. So I'll be focusing on this, and I'll give you some technical details and programmatic details. So LISA, as you can see here, is the only one that doesn't have the rainbow, because it's the only one that is not in the electromagnetic spectrum, because it's covering gravitational waves. So what is LISA? LISA, in fact, is the Laser Interferometer Space Antenna. It's an European Space Agency mission of L class, which means that it has a budget that will be around 1.5 billion. And will be launched, hopefully, in 2035. The goal, the scientific objective of this mission is to measure gravitational waves in space for the first time ever, of course. So now, I'm probably the worst person in this room to explain you anything about gravitational waves, because I'm a mechanical engineer, so. But we need some common understanding on that, just some basic things. So gravitational waves are waves of gravity. So we are all now sitting on some chairs because there is gravity. This gravity has some fluctuations that are due to gravitational waves. And we measure them, we can measure them by putting bodies, so like any body, in free fall. So these bodies are only subjected to gravity. They will start oscillating. We measure the relative distance, and by measuring the relative distance, we detect gravitational waves. What is the problem is that the change of relative distance is extremely small. So the change of distance given by galactic sources, so you have black holes, binary black holes, neutron stars, or things like that you want to observe. So then you need to be able to measure a change of distance that is 10 to the minus 21 times the actual distance. So if you have them at 1 meter, you need to be able to measure 0.20 after the comma, which is extremely challenging, of course. So like maybe some here in the room might argue already that we already measure gravitational waves, and that's true. So we have LIGO in the US and the Virgo in Italy, close to Pisa, that are these gigantic interferometers that use the same principle to measure gravitational waves, but they measure gravitational waves in the audio bandwidth, so roughly between 10 hertz and 10 kilohertz. These worked very well after like some decades of development. They were able to finally observe gravitational waves from, I don't remember what, I think binary black holes. And so yes, it worked, and a few years ago this was awarded with a Nobel Prize. So now, if we want to measure different frequencies, because at the end gravitational waves are like any other frequency, so you need to tune, like you tune your radio, one could say, yeah, then we built a LIGO and Virgo that observe the low frequencies. And that is theoretically possible. You just tune the technology, and then you say, you don't need to go to space. The problem is that if we want to measure something on the Earth, we have some disturbances already. Like we have waves, we have tides, we have the effects of our existence. So like we have trains, cars, people. Whatever we do is a source of gravitational waves. So we cannot observe gravitational waves from the universe, from the surface of the Earth. So then to provide insulation from these disturbances, we go to space. So that's the idea. We go to space. Once we put these free-falling bodies that I mentioned before, we put them in space. They will not see the effect of the waves of the sea. Point is that also here, so one thing, space is perfect insulation. In reality, also space has some issues because we have micrometeoroids, we have solar pressure, that is one of the main disturbances. We have thermal gradients, outgassing. We have a number of effects, so we cannot just put some heavy bodies somewhere in the solar system and measure the distance. We need to protect them from other disturbances that are coming from space. So then we put them in a box. We put them in a protective box. So basically, we put them in a satellite. The point is, once we have a satellite, okay, we don't have these external sources of disturbance, but we have other sources. So we are generating new sources of disturbances, which we need to control. So like the bottom here, the summary, let's say the final message is that we can observe gravitational waves in space. It is feasible, but it's not easy. And just to give you some numbers, if we go back to this 10 to the minus 21 figure that I showed you before, and we consider that if we build an interferometer like with a laser, we can probably stretch it to some million kilometers of distance, then it means that we need to be able to measure. We still need to be able to measure femtometers. So 10 to the minus 15 meters. So 0.00, a lot of zeros. So that's very challenging, and well, we'll see something more afterwards. So then, if we take one of these arms that I showed you here, in a schematic way, and we put it together, because we need to have more than just one to actually gain meaningful information from these gravitational waves. So the idea is that we don't have only one arm. We have three. I mean, two would be enough, but I mean, once we put 3 satellites, let's just do 3. And so the idea is that we don't have only 2 free-falling bodies, we have 6, 2 per each satellite. These satellites are at 2.5 million kilometers. I mean, they could be 5, it could be 1. I mean, it depends. It's still a bit to be defined, but they will be at some million kilometers of distance. And they will be using this laser interferometry to measure this very tiny change of position of these free-falling bodies. So if we look at a single spacecraft, again, it's a spacecraft. It has its own systems, and is shielding this body that is free to move, right, inside a special box. In reality, is even a bit more complex. So the body is in a box that has some electrodes. So because we don't want it to move completely in a completely free manner, we want it to move only along the sensitive axis. So we need to constrain even like the other degrees of freedom. So all of this is just to tell you that, again, this is challenging. And okay, maybe this is the most complex slide. The goal is that we need to reduce to mitigate the noise that is coming from the spacecraft and is coming from the outside of the spacecraft and is shielded by the spacecraft below a certain number. And we have 2 sources. One is the noise of the interferometer, so basically your sensor. How good is your sensor in measuring the distance? How much noise is giving? And how much noise you actually still have on your free-falling bodies because of these sources. And again, one of them is these electrodes that we need to have inside. It's electrostatic actuation, and this is noisy. So this is our goal. At the end, it goes back. It's a complex way to define these femtometers that I showed you before. So how do we know that this is going to work? Well, we know it because a few years ago we flew another mission that was called LISA Pathfinder.
9, 8, 7, 6, 5, 4, 3, 2, 1, top, allumage et décollage de VV06.
So this was LISA Pathfinder and was flown on a Vega rocket, one of the first launches. And basically it took one of the LISA arms, and instead of having the test masses at a million of kilometers, the arm was shortened to 35 centimeters, so that we could not get any information about gravitational waves, but we could estimate these noise sources. So, like, there were some requirements, and the requirements of LISA Pathfinder were a bit higher than the ones that we have on LISA, but still, the final results were actually already in line with what LISA is requesting. So that's a very good start. It means that we can do it. Actually, without this result, probably ESA would never, invest more than 1 billion to do something that maybe doesn't work. So now let's look at how LISA is done. So this is the spacecraft. So like the box, one of the 3 spacecrafts. So the core inside of each spacecraft is called MOSA, is the moving optical subassembly. That has these two, has this twin shape. So it has 2, now we'll see it in the next slide. So it has like a telescope that is collecting the light and sending the signal to the other spacecraft. Then we have an optical system that is doing all the optical processing, let's say, that we need. And then we actually have the part that is hosting the test mass that is called the GRS, so Gravitational Reference Sensor. that is the component that is hosting one of the free-falling bodies and is the main responsible for mitigating the noise in acceleration. So it's not the biggest part in terms of volume, but it's one of the most complex and the most critical. So here we have a rendering of this GRS. So the interesting part, I don't know. So the GRS is the Italian contribution. So Italy is paying for this. So here I have a rendering on the right, and on the left there are like some pictures of the system that was equivalent in LISA Pathfinder. Now we can see like another picture. So if you are a mechanical engineer doing renderings, it's very important. So you see this is the current design that we have for the GRS. And if we look at an open view, so the core is this test mass. So the free-falling body is a test mass, is a cube of gold, actually gold platinum of 2 kilograms. Is inside this box called electrode housing that is also in gold. It's gold coated, actually, and has these electrodes that we use to control the test mass. We need a bunch of mechanisms that are used. For instance, this is used for caging during launch because, well, you know, launch is quite tough, so you need to block the system that will be free during science. We have another system that is called positioning and release mechanism that is doing the same, but after launch. So it's constraining or setting in free motion the test mass once the system is in orbit. We have a charge management system. So because if the test mass and the spacecraft have a different voltage, this would create an attraction and noise. So with some UV LED, we illuminate the test mass and the electrode housing, and with some control we put them at the same voltage so that there is no attraction. And then we also have one of the other challenges is also the vacuum inside this GRS, because any particle that is inside will collide with the test mass and will give some noise. So we have a tube that is evacuating the particles to space. So one would think that space is already empty, but the point is most of the space mission don't really care about the level of vacuum. While here we need a level of vacuum that is relatively high. It's not super high, but is high. Because again, we would create noise otherwise. So now, if we look a bit at the programmatics, so as I mentioned before, the GRS. So to build a space mission, the main contribution is usually coming from the European Space Agency, but the European Space Agency is paying typically only the spacecraft. In this case, it's a bit different, but let's imagine that it's paying the spacecraft. Italy is paying this GRS with some Swiss contribution and a small contribution from the US. All the optical part is provided by Germany and the United Kingdom, and the telescope and the laser source are provided by NASA. Just to give you an idea, so this is the rough order of magnitude of the cost of each of these parts. You see the big chunk is the spacecraft, is the ESA part, and right now this is being developed in parallel in a competitive study between two companies. One is Thales in Torino, and the other one is Airbus in Friedrichshafen. And only one of them, well, it's a bit more complex, but only one company at the end will get this contract. So that's actually why, if you paid attention, so I cannot show you which shape, like the real shape of the spacecraft that they are using. So I put random shapes. So you see here it's round, here it's whatever, here it's a rendering that, I mean, they're all different, the pictures that I put, so that you don't know what is the real shape. And also this, in case. So now let's look at the, again, at the programmatic. So I said that this will keep us busy until 2035. So here are the different phases of the development. This doesn't have a laser. Well, I don't know. But so it does. Okay. Fantastic. So this is, so now we are in this phase here. So this is a preliminary design. Then there is the tendering process in which one of these two companies is selected, and also the national agencies are placing their own contracts for their own parts. Then there will be the final design, all the, the second part of the preliminary design, that is fun to say, the final design and fabrication, all the testing part, I mean the assembling and testing of the entire system, and then from here onwards you have the real mission for like 7-9 years, I don't remember. So this takes a lot. It takes a lot because each of these phases, okay, in the development process you have these, maybe you have seen it, you have this V-shaped development where you go from requirements to implementation and back. So here you start testing and verifying that you are fulfilling the needs. And again, how is this flown, let's say, from the agencies to the industry? So here I put a diagram. So you see, we are in this phase here. So you have the different space agencies that are doing their concept studies. Then, if the contract is very big, then they actually place some contracts for industrial studies. That is where we are now. And then at some point, you place the big contracts, and companies get the real money, and they start really working on that. So. And this means, so like this process that is a bit, you see, complex in a way, and also the fact that the work is split between various countries, means actually this, that, well, I didn't do the actual math, but we are producing more paperwork than actual hardware. So that's a bit the disadvantage of developing a space project. So the non-romantic part of space projects in at least the public domain. So here I put I put the level of requirements that we have from the top level, the mission requirements, to down to actually some components of the GRS. And each of these levels has, like millions of documents. So for instance, from May until June, we have a review for the payload that is called Instrument System Readiness Review. And this is just a list of documents that they sent that we have to write in the next month. Well, not me, but not all of me, luckily. So that it's really a lot of paperwork. So like this is important. So now back to some technical things. So what does it mean that we have requirements? So here I put an example of one of the requirements. So I mentioned before that, okay, 21. I mentioned before that the spacecraft around these free-falling bodies is introducing a disturbance in terms of gravity. What do I mean? I mean that once we put, so we're measuring something related to gravity, right? So if we have an object alone in the universe, fine, he will not see anything else. But if you have an object inside something else that is a spacecraft, the spacecraft will pull these free-falling bodies in a direction. So then we have like requirements that are defining the maximum gravitational pull that the spacecraft can have on each of these free-falling bodies, which means that once the spacecraft is designed, we will also design some calibration masses. So some masses will be designed and machined and tuned in such a way that the gravity has a zero value or nearly zero value. I mean, here you have the actual maximum number where these test masses are located. Okay, because, well, fine. Another example that I want to make here is how we go from this acceleration noise that you saw before. So this is actually directly linked to the fabrication tolerances, so like for mechanical engineers. So because the total acceleration noise has a part that is dedicated to actuation. Okay, we don't have actuation along the sensitive axis, of course, because otherwise we wouldn't measure anything. But we still have cross-coupling between the other axes. So so the sensitive axis is X. If we are pushing along Y, so the orthogonal direction, we may still see a force along X. And this is actually linked to the fabrication, to the assembly tolerances of this box, that is the electrode housing. So at the end, we can flow down from a top requirement. We flow down to a very practical requirement. So when you machine and assembly this box, your final tolerance must be within a certain boundary. So then this is basically all the work that is done when you develop a system of this type. You flow down requirements and then you split them between different companies or between different entities or different people. So now another thing, like, I don't know if for you 1.5 billion are a lot or not, I don't know. But typically are a lot, at least in terms of a project, not of course for a person is a lot. So and why do they cost so much usually, these public space missions? Because, well, technology is complex, so that's a high cost, and it's also public money, so you cannot you finish on a newspaper if you spend it in dinners. So high cost means that you really want your system to be reliable. So if you spend 1 billion and then it's a gigantic firework, people will not be happy, probably. So then you want this almost 100% reliability. So to have 100% reliability, also because you cannot send people, like you cannot send a PhD student to space to fix your satellite. Then you need to do more design, more testing, more redundancy, and this means that you have even more cost. So that's why the cost is high. And where does this start, actually? Why does the cost, okay, of course, technology is complex. If you are measuring gravitational waves, maybe technology is complex. But this also starts because a rocket is expensive. It's already some 200 millions. So already spending 200 millions, then you're already in this loop. So that's a bit the trap where we are with most of these projects. And a great or terrible example from a management point of view, at least, is the James Webb Space Telescope. That is working great in terms of technology and science. But if you look at this table, you see this is how the planned launch moved from 1998 until 2021. So here is the planned launch. You see that it moved up of 14 years. And the planned budget went from 1 billion to 10 billions. So this is unacceptable in most of the cases. I mean, here I don't know why, but we cannot do it. In Europe, we cannot do it. The project would die. And also here, it basically, like the James Webb basically took all the budget that NASA had for astrophysics. So it's a great mission, but basically took out all the air from any other space mission that you could conceive. So this is the risk that you're facing when, from a programmatic point of view, when you're working on these projects. So now, last two slides that I wanted to, last 2 points. So I mentioned this gravitational reference sensor that will be hosted inside LISA. So does it have other functions? Potentially, yes. Well, first, you can also call it inertial sensor, if you want, instead of gravitational reference sensor. The point that inertial sensors are used also for military applications, so we use a different name because, well, also this you cannot use it for military applications, luckily. but it has a couple of applications. At least one is so there was more than one actually. There were two missions that have been flown, GRACE and GRACE Follow-On, that have the same technology that measures the changes in gravity of satellites that are orbiting the Earth, so that you could see how gravity is changing with time. And by observing this change of gravity in time, you could see, for instance, here is the lack of water in California. Because the ground has lost so much water in time that you could see that the gravity there has changed slightly. And using the gravitational reference sensor will be like a further, let's say, advance of what was done in the previous years with these satellites. Then there was another application that maybe now is not relevant anymore, but NASA was saying that using drag-free, so a gravitational reference sensor, that means a drag-free satellite, a drag-free control, would reduce significantly the cost of operating a satellite, a constellation of satellites in space. So now we have a lot of constellations of satellites. This has not been implemented because most of the work is done, instead of having like very good sensors, you have very good artificial intelligence, for instance, that you put, it's like most of your phones now that they have like just an average sensor, but then very good algorithms. But anyways, there was this idea, and maybe this has never been fully implemented. Maybe it still has some applications. And then another last slide. So how is Europe doing, except on LISA? I mean, LISA is one of the most important missions that the European Space Agency is flying, because it's a unique technology that is maybe something that the US are not able to do in this moment. But anyways, just so I put here some points. So like, what is the idea behind these missions? Of course, is to create growth. You need to develop strategic technologies, and also you keep in Europe personnel, so engineers and know-how. But it's not doing great for different reasons. Of course, you have seen this process is very inefficient in a way, because you have to make everybody happy, and also because of the Russian war and some bad choices of, let's say, our politicians. Europe is losing access to space in 6 months. So, like, because the Vega has some issues, Ariane 5 will be retired, and Ariane 6 is not ready yet. So, this is a bit the situation in Europe. So, because of this accident with Vega C, I mean, it was the DG of ESA that said that we are losing access to space. While meanwhile, unfortunately, good for them, but the US, of course, are doing very like great things. So, like in this moment, Europe is a bit lagging behind. But 10 years ago, it was different. So things might change.
Have begun on the side boosters, so let's watch as they touch down.
Stage 2 is thermal guidance.
So this is what the US are doing while we are losing access to space.
What an incredible sight to see as we watch the side boosters touch down for landing.
So just to give you a bit the advantages and disadvantages of the process that we're using. That maybe for science is the best, but maybe not for technologies. Let's see. So this was my last slide. So if you have any question, I'm here. And otherwise, you can look at the orbit for like hours.
Okay, let's say that again. If you have got questions for Carlo, slide.do/spec50, spec50. It's quite interesting. While we gather a few questions, to tell you a bit of background story. Back in 2018, I guess a few people of you remember that. We had an event at the airport in Trento, and we invited Carlo. We didn't know each other. We sent him a message on Twitter because he was following Speck&Tech on Twitter. We're like, who's this guy? We sent him an invitation, and he turned down, and we are like, fuck, okay, maybe in 5 years. Yeah. So
I was stuck in Munich.
yeah, indeed. So it's great to have you here. So we got a couple of questions. First is like, how do you make sure that then a possible measurement is not detected as an error given by surrounding noise, considering all the noises?
I cannot answer that question. No, this is something that you have physicists that do their career on this. So there is a very complex data analysis. So I can tell you this, that if you consider LIGO is a noise-driven instrument. So you have noise, and then suddenly you have a signal. With LISA will be very different because as it is a low-frequency observation, you have that every source, you have these black holes that are spinning, so you continuously have a signal, but you don't have only one because it's not the black holes disappear. They disappear in LIGO because they are collapsing there, but in LISA you see them spinning. So you'll have thousands of sources at the same time, and how they understand this is a mystery to me. It can be done. I've seen it, but this is it's a good question because also we have some noise sources that are not just noise. It's like some transient sources. We call them glitches, and I mean there are ways, but don't ask me.
There's a question that actually involves you. Is this project this long just because of the number of players and bureaucracy involved? And could working under pressure and with tight deadlines cut time in two?
It is long also because of bureaucracy, but it's not that. I would say that is long because you need to test and retest things. So to make sure. In every phase, you're basically testing the same thing. So you have the engineering model and you do all the tests. You have the qualification model and you do all the tests. Then you have your fly models and you do all the tests. So like a lot of time is taken by tests. And actually, often this is like the pressure is very high. So people work with very tight deadlines, but then things are still delayed because there are issues and somebody is late because, of course, if this is done in-house in only one entity, then it's easier. But as this is spread all over Europe, then also sometimes interfaces are not fitting together very well. So there are multiple reasons. But of course, if you just do it in one institute, it will be faster.
You were telling about mistakes. So how can the mission fail, and what can go wrong in 12 years? Maybe it's easier to say what cannot go wrong.
One thing that is there are a number of single point of failure. So usually the space mechanisms are one of them. So if they don't move, then you're screwed. Also, these satellites will be put at millions of kilometers, but they have a laser, and they have to see each other. So you need a control system that makes them pointing the laser in the right position while orbiting the sun. And if they are not able to build this constellation, you have 3 satellites, for fun around the sun. So
There's a very technical question. I didn't understand. Like the question is, I didn't understand if it was necessary to build a void pump, or if it was simply just a way out of space.
No, it's not a pump. It's just
Una pompa vuoto.
It's not a vacuum pump. Well, it is, but it's not an active pump. It's just that the air is flowing to space. The point is what we do on ground. So we build this system, we put it in vacuum, and then we seal it. Then it's launched, and once it is in orbit, the valve is open, and the residual air is going outside. But it takes 6 months to get to the level of vacuum that we need.
Not bad. Okay. Was your GRS already built, like the one that was used by NASA to measure water in California, or you had to?
It's a different technique. So the one from NASA, the GRACE, is more like a more standard accelerometer, but it has a level of noise that is some order of magnitudes higher. So if you use, you don't have to use the GRS that I showed you, but you use a similar technology, maybe a bit smaller, a bit more compact, but then you can gain like 2 orders of magnitude in terms of sensitivity.
Got it. There's quite a few more questions, but we got the final one, which is also a funny one. I'm an engineer, and I was always told that G is simply equal to 10. Isn't it?
Well, for mechanical engineers, yes. For physicists, no.
Okay. Thanks a lot, Carlo.
Yes.
Warm applause. Okay, we proceed with our second speaker of the night, Linda Mazzotti.
Hi, everybody. Nice to be here. Happy to see you all. I'm Linda. I work for Primo Space, a venture capital fund. I'm going to tell you a bit more about Primo Space in a bit. I'm not an engineer, but I'm passionate about space business opportunities. And we operate in Milan, but I'm not from Milan. I want to specify I'm from Romagna. And I studied here in Trento a few years ago, so I'm happy to be here. So basically, space tech is very important for thousands of very invisible tasks that we need to manage in our everyday life. Of course, like classic examples like Google Maps or Uber for positioning, but many more. And it is also very important as like a piece of a puzzle that we need to solve in order to tackle very important crises that we are dealing with right now, like the war in Ukraine. Somebody said Elon Musk, like Starlink, sorry. And of course, also the climate crisis. And maybe in the future, space will also be the place where we decide to develop new materials, but also organs on chip, and food and wine, which is also something that people are working on right now. It's not something too futuristic. However, it is true that space has been always considered, I mean, in the last decades, as something very connected to space agencies. Of course, what Carlo said before, so European space agencies, the NASA, and everything connected to governments, the military sector, and defense. However, it is becoming increasingly appealing for business. In the last few years, of course, again, thanks to Elon Musk a lot, but especially because of three factors. First of all, the miniaturization process of space assets. So because of technical advancements, now it's possible to, before there were huge spacecrafts that needed like billions and billions to be built, and they were tailor-made. And right now, you can just launch a CubeSat in orbit, and it's a 10 centimeter per 10 centimeter thing, and it's big as a toaster. And you just send it in orbit, launching it on SpaceX, and the whole cost does not even reach 1 million, even counting the insurance. So it's totally accessible, let's say, more accessible. And also the space launch cost has decreased a lot. So again, SpaceX comes out, but there are hundreds of companies. Even in Europe, there are many that are trying to build micro-launching solutions. And one in Italy is called Sidereus, and they started from Naples. And they're trying to build a launcher, a nano launcher. They called it Razzo da Giardino, like a garden launch vehicle. But they have a very ambitious mission. They are trying to they make it available, the launching cost for 10,000 euros per kilo, which is super low. And the third factor I want to mention is the advanced space data applications that are now being developed. So all these technical advancements, together with the ambitions of entrepreneurs and innovators, have made possible, let's say, set a new chapter for space, which is also called New Space. And the new space economy has become totally attractive for private capital. And this is where venture capital comes into the game. So Primo Space is a venture capital fund. I don't know if here, like many of you know what a venture capital fund does. It's like an actor, a financial actor, that provides capital to a very specific set of businesses. So startups that are highly risky, but that have super high potential of scalability. So they buy a piece of a company, funding the company, of course. I give you 1 million, for example, and I take 20% of your shares, hoping that in 6 to 7 years, I will sell it back, maybe into the public market or to another company that wants to buy yours for a multiple of the value of that piece of the company. Maybe I bought it for 10 million, and then in 7 years, it will be worth 40 million. And that's a per 4. That's a very simplistic way of putting it, but more or less. So more and more companies, like financial actors, came into space, the space business, and top VC funds at the global level are now investing in space and have been investing in space in the past few years. We have Funders Fund. I don't know if you heard about these names. You have Kozla Ventures, 500 startups. Most of them are US funds, but now we're going to see there are even more. Space company received 45 billion in 2021. That was like a record year in funding. And last year, there has been a drop, unfortunately, but you know, the macroeconomic crisis is quite heavy, and they only received 22 billion at the global level. Yes, it's a bit, but the total value of the space economy was worth, estimated, of being more than 400 billion in 2022, and some studies estimate that let's say at the general level, all the space companies in 2040 will reach in revenues more than $1 trillion. And that's huge. And that's because of the business opportunities that I mentioned. So most of the actors are, of course, US-based, because US has like a bigger market. The defense and military sector has always been super active and very, like, with big pockets. But Europe is slowly trying to catch up. And these are only the funds that are active in the European area. And they were born a few years ago. So Seraphim was the first one in the UK before Brexit, so it's still considered Europe, maybe. Then Primo Space came after that in 2020. And all the others just joined right after 2020, so in the last 3 years. And there has been some kind of a totally not constant funding, but the trend is positive. Primo Space is the space tech dedicated venture capital fund in Italy. It is one of the main ones in Europe, the main one in Italy for sure, and the first one. And till 2020, we supported 11 companies, and they are all active in very different sectors. We have launch sector players, just like the one that I mentioned before, Siderius, but also Pangea. They're from Spain. So we invest not only in Italy, we can invest even abroad, of course. But then there are companies that are using space data for Earth applications, like Aeolian or Chai, that is from UK. Then we can talk about them later if you want. And I just wanted to mention ICO, because ICO has been the first company that we invested in, and they're active. They develop algorithms for satellite missions automations. I don't want to talk about ICO, but Mattia Varile will talk about it later on. And basically, this is what we do. I'm passionate about space business applications, but I'm sure that I believe that more people should be passionate about them as well. That's it.
Oops, okay. Thanks, Linda. There's no question that were explicitly asked.
Okay.
So it was kind of a good introduction to Mattia for his third talk. Of course, if you're interested in VC funding and whatever else she just told you, meet her in front of a beer. Mattia Varile, Icospace, on stage.
Okay, thank you. Hello, everyone. I'm Mattia. I'm Chief Innovation Officer in ICO. Nice to meet you all. ICO is a deep tech startup founded in 2017. And basically what we do is automating space mission. This is quite important because we can see that the complexities of the presented mission, the Lisa is one example, is increasing and will increase even further. That's why we think that artificial intelligence, machine learning, and automation more in general will play a big role in this transition. So we can consider two directions to follow in order to reduce the costs associated with space mission. The first one is, of course, to reduce launching costs. This is something that SpaceX is doing quite well. On the other side, there is another cost in a space mission that is instead operations. The operations is the cost associated with handling and managing these really complex assets. So, ICO, as I said, we already tested in space some technologies. We're reaching TRL 9. TRL is a scale that we are using for assessing the readiness of a specific technology. We already have customers, between the customers, the European Space Agency, the Italian Space Agency. We are in contact with a lot of companies in Europe and in the US. Other than this, we have investors. Primo is one of them. And we see a bright future in this direction because we get pretty good revenues, and we are seeing opportunities for growing even further. So as I said, we develop artificial intelligence for space. This is quite important because, as I said, we can reduce greatly what is the cost associated with space missions. And we can do this by using, again, artificial intelligence. And we have different products that we already have in the market. I will present today 3 of them that are the most promising in our opinion. But we will see also the research and development activities that we are carrying during these years. So our vision is to have an ecosystem of products that can communicate in order to achieve reduced complexities associated with space mission. What we are trying to do is something quite similar to what is happening already, for example, in the automotive field, in which automation and artificial intelligence is playing a huge role in automating, for example, self-driving car. As a parallel, what we plan to do is something quite similar for space. We want to create a sort of autopilot for satellites. And for doing this, we have 3 different areas that we want to cover. The first one is smarter satellite operations. This is algorithms and solutions that can be implemented directly on board of the satellite. The second one is instead a direction in which we are providing tools based again on artificial intelligence that can help instead operators on the ground. But there is also, we are also envisioning solutions that can help scaling up the ecosystem on constellation level, because we are seeing a lot of mega constellation, I don't know, thousands or even more satellites that are composing a constellation. A quite famous example is Starlink, in which we have 60,000 of satellites. And we see this as a quite important step towards the automation of the whole ecosystem. So as I said, I will present briefly some of the products and some of the technology that we are envisioning. So I will present Orbital Oliver, that is an automation library that can be implemented directly on board of the satellite. And then we have Cloud Charge that now is a cloud detection algorithm based on deep learning, but we are planning to expand these capabilities towards a full end-to-end solution for onboard data processing. So let's start with Orbital Oliver. So this is what an actual mission looks like. So we have first a planning. This planning is done on ground, and this planning is sent then to the satellite, in which we have the execution. So for example, if you want to take a picture of a specific area on the globe, you need to schedule this operation on ground, then send the instruction to the satellite, and then the satellite, for example, take the picture and send this to the ground. Then on the ground, you have to analyze this data, and you need to assess if the image that you took is aligned with your objective of the mission. This is quite time-consuming and inefficient, and we can reduce all of this loop, increasing the effectiveness of the space mission. So this is what I said, but basically what we are trying to do is to have multiple of the steps I was mentioning before directly on board of the satellite. So on the satellite, if you have intelligence, you have like a person that can discard and take pictures of the area that are interesting, and then can send to the ground just the information that are useful for the actual mission. So this is quite important. As I said, the Edge AI can help in reducing the costs associated with space mission. We can take decision in real time. We can have faster response to crisis. For example, if you have an earthquake or if you have a tsunami or something like this, you can take a decision directly on board of the satellite and send only this information on ground. This is where Orbital Oliver, that is our main product, envisions. We envision this software library on board of the spacecraft that can perform directly on the satellite the operations that are usually done instead on ground. Then we have our second solution that is instead Cloud Charge. Cloud Charge is I don't know if you're familiar with artificial intelligence, but it's basically a UNet, so it's a deep learning algorithm that can segment the clouds directly on board of the spacecraft. And by doing this, we can have a solution that can directly pre-filter information directly on board of the satellite. If you consider that like 40% of the data taken from the satellite are clouds, we can see that we have a really huge advantage only by using this quite, I would say, simple solution like a cloud segmentation tool based on deep learning. So we already validated to TRL9. The solution has been already flown in different missions. And we provide this package that a customer can simply plug and play on his device. So we have different. We balance the dataset in order to make this avoiding possible bias, avoiding introducing biases on the cloud segmentation task. And this is quite important because we want to generalize the capabilities of Cloud Charge to a wide range of data that we can that our customers can provide to us. So the last solution I will present today, again, product is a speedy scalar, which instead is an optimal routing algorithm. This can be run on ground, and basically what speedy scalar does is given a constellation of satellites and given the information that, for example, is produced on node A of this constellation, you want to compute the fastest track inside the constellation in order to transmit this data to another point. So it's a point-to-point communication, and you want to find the best path inside the constellation in order to perform an optimal routing. So as I said, we have a ground module in which you schedule all the contacts and you compute the fastest path inside the constellation. And then we have an onboard module in which we have, again, an optimized algorithm on the satellite that can achieve and can control the routes inside the constellation configuration. So now let's discuss a little bit about the research projects we have at the moment inside the company. The first one I want to present today is SAR data processing. So SAR is a synthetic aperture radar, is a particular type of Earth observation payload that is not affected, for example, from clouds or lighting condition, because basically what it does is projecting radar signal on ground, giving them bouncing to the sensor, collecting this data, and then trying to reconstruct the image directly on board. This is quite challenging because basically what we see on board of the spacecraft is something like this, and getting to this from this to this is quite difficult. You need a lot of computation for doing this. And what we instead are achieving is a deep learning based algorithm that can do this directly on board of the spacecraft. This is quite important because by enabling this data directly on board of the spacecraft, we can directly detect, for example, objects on the spacecraft, and we can perform something that is not available at the moment. So for example, we can perform tracking of objects on ground that is not possible at the moment using the current technology. We already tested this solution together with Thales Alenia Space, not in orbit, of course, but we are trying to find an opportunity for testing this algorithm on board of an actual mission. We have the help, of course, of the Italian Space Agency for doing this, and we hope in next 1 year to test this technology on orbit. The other quite important branch of research that we have internally is telemetry analysis. You have to imagine that, for example, a spacecraft can produce up to 1,000 of data streams for each second. So it's quite important for an operator to understand the patterns in the data in order to find possible anomalies and find possible things that can go wrong during the mission. That's why we are developing, again, a machine learning-based approach that can perform telemetry analysis and anomaly detection directly on board of the spacecraft. Doing this, we can reduce, for example, the possible failure of components, and we can mitigate possible things that can go wrong during the mission. We already tested this solution together with Thales Alenia Space, and with OneWeb we have an early access program in which we are trying to test the technology and assess the fit with the market, basically. Yeah, this is a run of the... Okay, now let's get to the autonomous GNC. Specifically, what we call ISAC is an ongoing research that has the objective of automate maneuvers directly on board of the spacecraft. So we have this control module that can manage the orbit change during the operational phase of a space mission, and this is based on a reinforcement learning approach that can optimize the thrust associated with the propulsion system that we are targeting for the mission. So what we found is that this approach is quite robust in our simulation environment, and we expect to see this approach quite robust also in space. Of course, this is an R&D project, so there is a gap between the R&D and the actual deployment on a spacecraft. But we see this research quite interesting. And specifically, the use of a reinforcement learning approach has a different impact on a wide variety of use cases that we are analyzing right now. So an example is autonomous landing. I will show you a brief video regarding this. But also we can foresee, for example, constellation of satellites that can autonomously reconfigure themselves in the constellation in order to adapt to the specific mission objective. So if you want to cover a specific area of the Earth, you can readjust the configuration of the constellation, maximizing the coverage of a specific area on ground. And this is what I was mentioning. So it's a constellation management tool that can provide an optimal coverage of a specific area, so local coverage, or in case, for example, of telecommunication mission, we can provide global coverage, optimized global coverage in a specific area of the globe. Then we have another research project that is Marla. Marla is basically a planner that can be deployed directly on board of the spacecraft. Again, we are using reinforcement learning because our vision is in a multi-agent environment in which we have all these reinforcement learning trained agents that can optimize the schedule and the plan during the mission phase of the constellation. So what we started on is by doing a simple downlinking optimization routine based on reinforcement learning, but we are now exploring an onboard operation planning optimizer that can optimize, again, as I said, the operations on board of the spacecraft, getting then to a multi-satellite task management in which, for example, each node in a constellation can exchange tasks and optimize the overall capabilities of the constellation. And our big branch of R&D project is, of course, computer vision. So we are seeing the computer vision task as a quite interesting topic to explore for different reasons. So we can deploy this computer vision, for example, for detecting objects. It can be on Earth observation mission, but it can also be on asteroid missions, or on moon missions. And we see this as a quite important step towards an autonomous pipeline to deploy on board of the spacecraft. Another task that we are trying to solve is segmentation, again, as a building block of an image processing pipeline that we can deploy on board of the spacecraft, and the key point detection. This is some example of the heritage that we developed during this year. So we, as I said, we used the TRL9 in different pieces of the computer vision building blocks I was presenting before. We already tested in Athena, for example, for an asteroid navigation task, some computer vision capabilities. And we get really good results on, for example, terrain segmentation using a multitask learning approach, and in rover navigation on Mars in this case. So for visual navigation, as I said, we have here some example of the tasks that we solved by using visual navigation and computer vision. The first one is relative navigation with respect to an asteroid. So you have the asteroid, and you want to understand where you are with respect to the surface of the asteroid. And for doing this, we are using a lot of computer vision. Specifically, we are using simultaneous localization and mapping that is currently used, for example, in drone navigations, but we are trying to reapply this technological stack also in asteroid navigation. Similarly, we also explored the pose estimation problem and the navigation problem. I will present this problem in the next slide. And we are also leveraging deep learning for visual navigation. For example, in a project together with Masten, we were trying to create an algorithm that was capable to assess the risk of landing in a specific area of the moon. So one big branch of the research that is currently active, and we see also a lot of traction from the industry, is satellite navigation and pose estimation. So pose estimation is basically, given a target and the chaser satellites, we want to assess the pose of the satellite that the camera is taking picture of. So for doing this, we have developed a lot of heritage, starting from the avionic project, in which we developed a deep learning-based pipeline, in which we have different steps in the pipeline. The first one is, for example, detecting the object. Then we crop the object to the frame to the object that we are detecting, and then we are performing a key point detection task. After this, because we are knowing already the model of the spacecraft, we can perform a 3D regression given the 2D projection of the key points. And by doing this, we can then extract the actual pose of the spacecraft. We see that this approach is quite robust if compared with commonly used computer vision task, and we see this as a first building block towards in-orbit servicing scenario, for example. So in-orbit servicing is given, again, target and the chaser, you want to service the target. So you want to replace a specific piece, or you want to change a solar panel. And for doing this, we need this technology that has been already demonstrated successfully in other domains. So for autonomous landing, as I said, we developed a multitask learning approach together with Masten and a US company. And we get to Jolly Juno, that is our first research project in moon landing and scenario like those. And basically what we were capable to do is to assess, as I said, pixel by pixel in an image, the hazard associated with the specific area of the target that we are trying to estimate of. And then finally, I will present the autonomous moon landing algorithm that has been trained using reinforcement learning. This is a thesis project that we carried on together with a student from Politecnico di Torino. So we are seeing the inference time of a lander that is trying to get to the target, and has the control of the thrusters on board of the lander, and has been trained using, again, a reinforcement learning approach. In particular, we use a curriculum learning approach in which we are getting to more complex tasks to achieve, and this is the results. So we get a pretty accurate reinforcement learning control algorithm that is capable to get to the target, I would say 95% of the time. Of course, there is a room for improvement. And yeah, this is it. Thank you for the attention. If you have any questions.
Thank you for your presentation. We have some questions for you. So first one, is a speedy scalar just based on this Dijkstra algorithm?
Yeah.
Where is AI involved in that?
So the AI is involved mostly on the onboard module that we are looking for. So we have an optimal planner that is capable to understand where to redirect the information on board of the module. But of course, the ground module is based on a Dijkstra and A-star algorithm that is quite common. Of course, we are also exploring, again, I don't want to be repetitive, but a reinforcement learning approach that we saw is quite robust in changing in the configuration of the constellation. But this will be in the future a machine learning approach. But for the moment, most of the machine learning is on the onboard module.
Okay. And then what's the relationship between your edge AI solution and the hardware limitation on the satellites?
So, yeah, this is a good question. We see that for the future, there will be for sure hardware accelerators for machine learning algorithms. This is quite sure because we already see this tendency in the industry. And of course, the limitation are we have a lot of limitation in terms of computing. But as Linda, for example, was presenting, we have a lot of new space companies that are adopting state-of-the-art hardware platforms, and hopefully in the future we will be compatible with these solutions.
Okay. Then there is like a economic business question. I don't know if you can answer to that, but how much did Primo invest in ICO, and what was the agreement? If you can,
I don't know if I can disclose this information.
Okay.
Okay.
Let's ask Linda.
Primo Space invested in 2020. As I mentioned, it was the first investment we ever finalized. So, like the first we finalized. So it was 1.5 million.
Okay. Quite a lot. Which are the technical requirements for the software that runs in space? Like the obligation of avoiding recursion, or there are other constraints, like for...
Yeah, this is quite true for really huge missions, for example, but the new space economy and new space companies are relaxing these requirements, getting to a wider adoption of innovative approaches applied to space missions. So again, we can boost the innovation in the space field by leveraging new space economies and new space companies that are using these new approaches for testing technology. This is quite clear, for example, for SpaceX, in which they're launching things without knowing if they will work, but yeah.
Cool. Then there is a machine learning related question. So did you write your own framework for to build and train your model? And if it is true, is the framework open source or like open to?
No, of course we are relying a lot on open source solution for developing machine learning models. TensorFlow, PyTorch, and so on are quite node solution. What we develop internally is instead an optimization pipeline for different hardware platforms. So we have as an output from TensorFlow, for example, a machine learning model. Then we can optimize this machine learning model for different types of hardware platforms. So we are compatible, for example, with Intel Myriad, NVIDIA Jetson. We are compatible with Google Coral. We are exploring a lot of FPGAs. Of course, this is closed because it's quite important for us to take the ownership of this technology.
Of course. And then the last question, how do you deal with software updates? I mean, you have your software running on a satellite and you want to update that. How does it work, basically?
Yeah, that's a good point. Is an open challenge for us. I want to be clear on this. But on a software standpoint, it's quite simple to re-upload the updated software or the updated model on board of the spacecraft. Of course, you cannot close the loop, such as, for example, on a DevOps pipeline in which you are re-updating the model every time, but we can foresee to closing the loop with the satellite. I will say one in a month to update the capabilities of the machine learning model that we are deploying on board.
Okay, thank you. That was the last question for tonight. A big applause for Mattia.
Okay, we'll do things a bit different tonight. We'll be very quick, I promise. But just to tell you, it's 11:08, and we had 3 talks. So congratulations to all of you for being punctual. So warm applause for being here. 10:08. What do you say?
You said 11.
11. Okay, it's 10:08. But time flies when you enjoy. Okay, so thanks for being punctual. And it's quite interesting to say that on Wednesday, it will be our 7th birthday of Speck&Tech, and celebrating with the 50th event named To Infinity and Beyond is quite promising. So thanks a lot. So here is where we cut the video on YouTube.